Welcome to Quantum Curious, and in today's video, I'm going to discuss the main purpose of quantum cryptography, that is to securely transmit message from one party to another. So how can we do this and how it is done usually in quantum cryptography or in quantum key distribution in general? We will see that the case in this video. And we will discuss some of the information theoretic protocol in this video also. So, first start with the kind of a motivation that we want to proceed further. So we have again our famous protagonists, Alice and Bob, and they want to exchange messages with each other, and the message are very kind of private, and uh, they don't want to another third party to listen into their messages. So they are afraid that there is a malicious party or a malicious person called Eve, and the Eve is also very interested in their message exchange and wants to listen to their messages. So Alice and Bob wants to devise a way in order to securely send their messages to each other. And even if Eve gets the chance to uh, intercept some of the messages, she will not be able to decipher what kind of messages Alice and Bob are trying to send to each other. So that is the whole purpose of quantum key distribution. So we will consider that we have for the case keys, secure keys, and these keys are absolutely random. And Alice and Bob are using these keys to transmit some messages over some kind of channel to each other. So that is the whole process of quantum key distribution, and that is the whole purpose of quantum key distribution. So for that case, for the time being, we will consider that the Alice and Bob has keys, and they are using these keys to transmit the message to each other securely. So in 1940s, Claude Shannon laid the foundation of secure communication, and this is the time even before the idea of quantum key distribution. So he proposed that there should be two functions uh, in order to uh, convey the whole message from one party to another party securely. So the first person is the encryption function, and encryption function uses the message and the key to come up with an encrypted text, and it is also called the ciphertext, and it is absolutely random and usually independent from the message. And there is another function used by Bob for the receiving party is called decryption function, and it uses uh, the encryption text and the key in order to decode the message that has been received by the receiving party or Bob. So here you can see that we have Alice, and Alice is using the key and message to encrypt the message into a ciphertext or encrypted text, and she is sending this encrypted text to Bob, and Bob has the same key as Alice, and he is using that key in order to decode or decipher the encrypted text. So this is the main mechanism in order to transmit the message securely to each other. So there are two conditions that should be satisfied in order to the protocol to be valid. So the first is the correctness condition, and it states that the message sent by Alice, that is the encrypted message, should be uh, should be decipherable by Bob, because Bob should have the same key as the Alice that she has used in order to encrypt the message. And the second condition is the security, as the message and encrypted text should be independent of each other. So even if Eve gets the chance to intercept the encrypted text, she will not be able to decipher it, because she has no encryption key that Alice and Bob are using, and the message intercepted by Eve would be completely useless for her. So these are the two conditions that should be satisfied by any cryptographic protocol. So another theorem states that the key that Alice is using to encrypt the message should be as long, or at least as long, as the message length. So let's read that carefully, that an encryption scheme can only be perfectly secure and correct if the number of possible keys is at least as large as the number of possible messages. So key should be at least as large as the message. So if we have, for example, message in form of the bits of 0 and 1, and the bits length has about 6, and so key should be at least 6. It could be longer, but it should be at least 6 bits in order to fully encrypt the message. So there's one information theoretic protocol that is called one-time pad, and that can be used to to securely deliver the message from Alice to Bob. So consider we have message M, and it is in the form of bits of 0 and 1, and similarly we have key that is also in the form of the binary bits, and both have length n. So Alice could encrypt the message in one-time pad by the XORing the message bit and the key bit consecutively, and come up with an encrypted message, that is E. And similarly, Bob can use again the XOR operation to uh, decipher the message, that is the encrypted message that is sent by Alice. So Bob is again using the same key as Alice to decrypt the message, and again using the same XOR operation to decipher the message. So this is the whole process about the one-time pad, and it is considered to be uh, one of the information theoretic secure protocol. So there are some conditions that should be followed in order for one-time pad to be valid and to be secured. So we have seen that the one-time pad is correct, because Alice and Bob are able to uh, send a correct message to each other. So is it secure? So in order to be secure, the encrypted message should be uniformly random in from the point of view of Eve. So, and it is also should be completely independent from the message. And you may be wondering that how could it be, because encrypted message is just the X is just obtained by the XOR operation of message bits and the key bits. So let's see how it could be. So consider we have an encrypted text, that is E, and it is uniformly random, as it could be seen by this probability distribution, that is 1 by 2n, and it is all for fixed message, and we could see that the encrypted message is given as this. So using the Bayes theorem, we could prove that the the probability of message, that is M, and probability of encrypted message that could be intercepted by Eve are independent. So in that case, message and encrypted text are independent of each other. And we will see later in uh, upcoming videos or upcoming lectures that we can use privacy amplification scheme in order to get more refined form of security and more refined form of message that it has negligible amount of Eve information. So we will see it later. So consider now we want to get more nearer to the quantum one-time pad. So in order to uh, touch that formalism, have to we will have to make some modification in our present protocol. So consider we know that we could write any bit that is 0 and 1 in form of a pure quantum state, and we could build a density matrix from it. So we know that if the key has 0 bit, the bit is that is the message bit is not going to be flipped. And if we have key bit 1, the message is going to be flipped. So in order to show the flipping operation, we use the bit flip operator in standard basis, that is the X operator. And it is also the same Pauli X matrix. So in order to get the whole scenario, we um, build the density matrix. So it is a joint density matrix of key and message. And we could see that if the key is 0 bit, there is no operator or no operation of bit flip on the message. And if there is a 1 key bit, uh, we are going to have the bit flip operation, and it is represented by X. So we could see that overall a message state could be written as the maximally mixed state, and it could be verified if we use message 0 and message 1 here. So we could see that a message is going to be maximally mixed or uniformly random from the point of view of any entity that is not holding the key as the Alice and Bob are using. So this is the desired form that we want to transmit over the channel connecting Alice and Bob. So now move on to the quantum one-time pad. We have seen that how can we use the 1 key bit in order to encrypt the message in classical one-time pad. So let's see what the case is about in quantum one-time pad. So we have some operation that we have seen, the bit flip operation, and that we are going to perform if there is the key bit 1, and if the key bit is 0, we are not going to perform any bit flip operation. So we have seen that we could employ the X operator in standard basis in order to have bit flip operation. So if we apply these bit flip operator in standard basis that we have used in Hadamard basis, we are not going to have any effect on the value of the bits, because in that case it acts like a phase flip operator instead of bit flip operation. So in order to get that done in Hadamard basis also, we are going to use the Z Pauli matrix, and it acts as a bit flip operator in Hadamard basis. So we could see that in order to encrypt the message fully in any basis, we have to use 2 bit of key in order to encrypt 1 bit of message. So it is opposed to it is opposed to classical one-time pad, as we have seen that in order to encrypt the message, only need one key bit, but in that case we need 2 bit of key in order to encrypt the message. And we could see that this is the case for the qubit, because qubit could be written as superposition of two states in any basis. So in order to encrypt both the bases, we need to use the two bit of information. So that is the uh, a difference between quantum one-time pad and classical but one-time pad. So we could see that we could apply any kind of information or any kind of operator on our state, and we could rotate it uh, in the block sphere. So that is for today. We have seen that how can we use the one-time pad and the conditions that should be followed by one-time pad in order to be a valid protocol or valid cryptographic protocol. And we see the difference between quantum cryptographic protocol and the classical one-time pad, as we need 2 bit of key in order to encrypt the message in quantum one-time pad, as opposed to only one bit of key in order to encrypt 1 bit of message. So that is for today. If you like the video, don't forget to like, share, and subscribe to Quantum Curious.